Many of the laws of mechanics we've met previously are wrong. They're wrong because they don't obey the laws of special relativity. If we change inertial reference frames, they don't transform the right way. One of the more efficient ways of fixing that is to put them all in terms of 4-vector quantities. If we have 4-vector relationships, then by definition, because the 4 vectors transform the right way as we transform between reference frames, then all our laws of physics are going to transform the right way. So though if you write them in tensor and vector form, everything works automatically. So we've looked at the position vector. The position vector in 4 vectors is automatically a position in space-time, not just in space. So you have events where the time and the 3 spatial coordinates. And we saw that the interval, the inner product, which is a scalar quantity and therefore also invariant between different choices of inertial reference frames, is a physical quantity in that it defines the proper time of an object traveling through space. So that's position. What about velocity? How do we normally define velocity? We have 2 equivalent approaches to a definition of velocity. The first is as a tangent vector to a world line. So if you take a world line like this in space and you take a tangent to it, then you end up with a vector. If you take a tangent to a 4-dimensional vector, then you're going to end up with a 4-vector. Another way of getting it is to take the time derivative of the position vector. So that looks like a perfectly good 4 velocity. However, there is a problem, and the problem is that while this quantity here is a 4 vector and therefore transforms the right way when we change reference frames, this thing here, the time, unlike Galilean relativity, where time is some big universal thing that never changes, as we change reference frames, this is going to change. So while this bit will change like a vector, this thing here will not. So we need to take the differential with respect to something that is a scalar quantity, something that is not changing as we change reference frames. And therefore, we choose to take the derivative with respect to the proper time. And so we define our 4 vector, our 4 velocity is defined as the rate of change of the 4 position with respect to proper time. And because we know this, we can just take this derivative, and instantaneously we know the relationship between the proper time and the coordinate time is just related by a factor of gamma, where these velocities are simply the time derivative of the position coordinate with respect to the time coordinate in whatever coordinate system we're using. And this is the instantaneous velocity, the total velocity, from the sum of the squares of these velocities. So there we have it. If we look at that, this is never identically 0. So even if our particle is completely at rest, and so these coordinate velocities are all 0, so we might be in the instantaneous rest frame of the object. This gamma is 1, these are 0, but we still have this c here. What's going on there? Well, in the instantaneous rest frame, we're still moving in time. And so the thing is still sitting there at time. And so in some sense, you can think of the 4 velocity as you're either moving in time or a mixture of time and space. Okay, what about acceleration? Acceleration is a fairly simple step from there. We need it to be a 4 vector. We need it to transform like a 4 vector does as we change between reference frames. And so we can take our velocity, which is definitely a 4 vector, and we have to take the derivative of it with respect to something that's a scalar. And so again, we just take the proper time, where this velocity and this acceleration vector are the 3 vectors for this velocity and the equivalent acceleration. Now gamma of v varies quadratically with v around v equals 0. So in fact, in the instantaneous rest frame, these derivatives of gamma with respect to time are both 0, and gamma is 1. And so in fact, what we have is we have something that looks just like the normal 3 acceleration near the instantaneous rest frame. So in other words, at very low velocities.